All right, thanks everybody for the opportunity to present our work. So I'll be giving a brief overview of geological carbon storage, and it'll be quick because I got 15 minutes here. So this is the problem. Heavy industry and utility sectors emit roughly 24 megatons of CO2 every year in Ontario. Of course, the big emitters are steel mills, oil refineries, natural gas power, cement, plastic industries, and all of these industries produce things that we need. We're not going to stop using steel, but a lot of them aren't really economically viable in a carbon tax regime. So this, along with, of course, a certain orange maniac, may lead production to relocate to other jurisdictions. So if we want to prevent this from happening, while also reducing carbon emissions, one of the things that we're going to have to do is capture and inject CO2 into deep formations. So perhaps that is the solution. So geological CO2 storage works in deep saline aquifers. It's been demonstrated worldwide, and since 2015 in two projects in Western Canada, the Quest project in Alberta and Aquastor in Saskatchewan. And Quest has been capturing and storing 1 million tons per year since 2016. So the Cambrian formation, next. So the good news is that there is an extensive basal Cambrian sandstone aquifer in Ontario, and it is at depths that are appropriate for the storage of CO2. And when I say appropriate, what do I mean? I mean that the pressure and temperature conditions are such that CO2 will be in a liquid or supercritical state once it's in place. So that's not to say that everything is perfect, but in any case, there's an opportunity potentially. Currently, the best published estimate for capacity in this region is on the order of 700 megatons, but estimates vary widely. Current evidence suggests that the basal Cambrian in Ontario is less porous and permeable than in the Alberta Basin, but that's not to say that it can't be used. What we do have that's probably better than in Alberta is very good cap rocks. So they're thick, continuous, very impermeable, and we have a pretty good understanding of these cap rocks. So that is good. Not going to say anything more about cap rocks, but so this shows you the wells penetrating the Cambrian. So while there are, as you can see, quite a few wells that go that deep, good quality geophysical logs or petrophysical testing of core is less prevalent. So there is a bit of a sparse data problem to date. What we do know, going back. Well, I'll just skip ahead because I think there's some missing slides. In any case, what we can say is this is a little look at the basal Cambrian. That's kind of what the rock looks like. It was deposited after the breakup of supercontinent Rodinia. Don't ask me about that. That's Lauren's part. So global sea level rose, and that flooded the Laurentian craton and formed shallow seas, and that's where you got the clastic deposits that are now sandstone, primarily quartzose and arcosic. And then as you get shallower in the basal Cambrian, you get more dolostone or dolomitic sandstone, that sort of thing. So you can see in the middle a simplified stratigraphic column, and on the right you can see some facies that are observed in core. So hopefully the dots on this plot actually are visible. They're a little faint. Apologies for that. But this is what we know about permeability and porosity. So we have data from core testing in about 22 wells. So of all those wells, 22 have core, and we have about 1,000 measurements. So at the high end on this plot, those are pretty good numbers, and they represent relatively clean sandstone. On the low end, that's dolostone or dolomitic sand, so not very permeable, but there is some permeability there, and it varies a little bit regionally. If we take the same data and organize it as a histogram. That's what it looks like. And if we put the units in hydraulic conductivity for the kind of groundwater people in the audience, you can see that this would be kind of considered a poor aquifer, at least if you took the average over the entire area. But it's still permeable enough to permit carbon storage because you're injecting a low viscosity fluid at pretty high pressures. Speaking of injecting, injectivity index. So I'm just going to talk about this really quickly, and it shows up there. Yeah, so this shows the injectivity indexes, which is essentially an index describing the rate of CO2 injection that can be achieved at a given pressure increment. And so obviously it's highly related to the permeability and thickness, and it's been shown empirically to follow this relationship. If we plot some Ontario numbers on there, we can see where they show up on the plot. And so that's based on the permeability thickness at those locations or kind of in those regions on the wells that we have. And so, we're in the mix. We're certainly not up at the, Quest level, as I said before, but, it's not beyond the bounds of reason that we could do this here. There's a number from Quebec. Probably skip over that. But it's based on even much, much less data than we have in Ontario right now. But they are talking about trying to inject CO2 there as well. So this index is interesting. But beyond a minimum threshold, it may not be the primary constraint that we have to consider, because really our limiting factor, if we're limited by injectivity, we can put in another well. There you go, you doubled your injectivity. But what's really going to limit us is going to be pressurization. And that may limit the capacity overall. So I'm going to look at a little bit of modeling. So it will be a simple model, well, simple in geometrically, but pretty complicated in terms of the physics that are in there. So that's what the model looks like. So this model is radially axisymmetric, so geometrically simple, but we can look at key physical processes here. And yeah, all my more complicated models are under NDA, so this is what you get. That's what it looks like, a very simple 2D model. Layering and properties in this model are broadly representative of what we might expect in Ontario. In the basal Cambrian, so this is only the basal Cambrian represented. Cap rock is just assumed to be impermeable here. The range of permeability here is similar to the histogram presented earlier. It represents a typical stratigraphic sequence observed in Ontario basal Cambrian with lower permeability as we go shallower. And now we'll look at a few model results. In the upper left, we have the CO2 plume. Nothing has been injected yet, so there's not much to see. On the bottom left, lower left, we have pressure change. So even though we've injected very little, you can already see a little bit of pressurization. And then on the upper right, you'll see a mass injected as we move along. And on the lower right, pressure again just plotted up in a different way. And so if we move ahead, so this is after 2 years of injection, after 5 years of injection, after 10, 15, and 20. So the main point here is that we can see the CO2 plume even after injecting a pretty substantial amount of CO2. I think we're at, what's that say on the plot? I forget at this point. Anyway, millions of tons. It's got a radius of about 2 kilometers, but you can see the pressurization spreads a lot further. And why does pressure matter? Well, of course, if you pressurize too much, you could cause flowing wells, brine coming out of them, induce seismicity, and of course, this is our capacity limit. If you've got a lot of closely spaced wells that are pressurized, you'll soon lose your injectivity. And so, why does it pressurize so much? Well, it really is because the low compressibility of the sandstone aquifer. Quickly just come back to this injectivity index because it's kind of interesting. If you plot up our model results on there, you see that they're within the error bars on this empirically derived index. So that's just a sort of a side note. So we're going to come back to this plot now. And on here, this is the same model result here that we're looking at. And I've plotted up a few things. Focus on the plot on the right. So on there you can see the plume edge is plotted up, and there's something called the AOR. What is that? Essentially, it's the area where the effects of your project could influence human health. And in this case, I've defined it as the area where a certain threshold pressure is exceeded. That threshold pressure approach, you can look it up in the EPA's Class 6 well licensing. But in its essence, what it is the area where the brine has been sufficiently pressurized that it could invade shallow aquifers if a permeable pathway were present, such as a poorly abandoned well. So just coming back to this area issue, so we can see here that the plume is roughly 12 kilometers squared area that you'd be like, okay, this is where the CO2 is. But the area where you have pressurized brine exceeding the threshold pressure is 180 square kilometers. That's huge. So throughout all of that area, you're going to have to consider, maybe remediating poorly abandoned wells, certainly some sort of monitoring system. And yeah, not only that, this very large pressurized area will have a profound impact on the required offset between injection wells. So yeah, once again, compressibility is our issue here, and that's why we get such a big area that's pressurized. So if we move along, just have a quick look at another thing. So maybe this is wrong. We actually don't know that much about the overall kind of regional compressibility of the Ontario Basal Cambrian. It's hard to measure. One thing that could affect it is gas saturation. So this is just an example where I assume some very low residual gas saturation, kind of averaging on a regional scale. And you can see that only 2% gas saturation, that means 2% of the pore space is full of gas, reduces your area of review by a factor of 2 because it's so much more compressible. If you go up to 10%, it has an even greater effect. I'm going to skip this in the interest of not wasting time and just sort of summarize this hydrogeological challenge, which is, so we have a prospective reservoir. There hasn't been sufficient exploration for certain parameters, especially things like compressibility. So the error bars on any of our model estimates are pretty large. We need more information. Things like gas saturations are important. And, but I think based on what we know, you will need quite a few wells to store a significant proportion of Ontario's emissions. So I think here I put the estimate of 20 to 50 injectors for 10 megatons CO2 per year. I'm going to skip this slide and just flip to what is Ontario doing. So kind of two things. There's OREG 42523. This allows for permitting of pilot or demonstration projects for carbon storage. I would say it's loosely modeled on the Quest project right now, and I'll get back to that in a sec. The other thing that's happening is Bill 228, which permits commercial scale carbon storage. As mentioned, we're now in an election, and unfortunately this bill has only been through first reading and is now suspended. So yeah, I don't know when it'll be back again, but hopefully soon. I do think the government is trying to move things ahead, but I don't know if they're really succeeding so far. So OREG 425, if you look here, this is just a flow chart showing the process, and that doesn't even get into the requirements for all the various technical reports and assessments that you need. So it's quite an onerous process just for a pilot project. And the one thing, I think it's because they've looked at Quest and said, well, they had to do all that. But the Quest project is 10 million tons. No pilot project in Ontario will be that kind of tonnage because two reasons. Quest got hundreds of millions of dollars of government funding. Other reason, there was a source of CO2. In Ontario, there's no sources of CO2. You have to buy it. If you're doing a pilot project, you'll have to either truck it in or bring it in on rail before you inject it. So it's a much different scale of project that I think will be permitted under this regulation. And I guess the main point here is that so far I don't know that a year later that any projects have gotten through this process. So or even gotten maybe past step 2. So a quick flip to Bill 228, and I'm running out of time, but there's a couple interesting points in here, and I think these points I think are difficult for pushing CO2 forward in Ontario. So point one, proponents must store a minimum amount of CO2 produced by a minimum number of emitters. So that's making things complicated. Now you've got this rather difficult geological problem. You've got, a lot of uncertainty there, and now you've got to cooperate among various entities. That's a requirement. You're also going to be required to get a municipal endorsement, which is effectively a veto. That could be a real problem. And as the bill is written now, kind of it defaults to pore space rights being part of the surface rights estate. So when you remember those big areas of influence, you could have to negotiate licenses with potentially hundreds or thousands of property owners. And so I think all of these things are not going to be easy things to solve. I've kind of run out of time. I wanted to flip back. Anyway, the political challenge in Ontario. So there is a lot of CO2 emissions, and we could be making our own industry uneconomical and kind of get decarbonization by deindustrialization. Doesn't mean the carbon's going to go away. It just means it's going to be emitted elsewhere. Cambrian's a viable target potentially, but there's insufficient exploration, and we need more exploration. But of course, with this very uncertain environment, it's hard for companies to commit to funding these projects. Arguably, OGS maybe should be considering drilling and testing some wells and trying to reduce the geological uncertainty. And that rig there is the first and still the only CO2 storage exploration well drilled in Ontario, and this program was carried out in 2022, and geothermal was part of that. Thank you, and apologies for going over time a little bit.